Hey, my name is Joseph Key, and today I'll be sharing with you about my Mechanical Engineering Senior Project, which is the Drone Payload Storage and Release System, or DPSRS for short. And so the purpose of this project was to create something that is able to attach onto a drone and can carry packages, but is released completely mechanically using the drone's built-in camera. And so what we're going to be covering today is a little bit of a summary of this entire project, which includes analysis, requirements, construction, testing, results, budget and schedule, among other things. So without any further ado, let's jump straight in. The primary ground rules for the entire project were the initial requirements. And so this project had 11. Once the requirements were established, the analysis portion of the project began. Analyses can be divided into three main categories, and that is structural strength, kinematic, and mechanical design. So an example are in analyses B and U. And just as far as a summary, these are both working on the grappling arm structural optimization. So it's the arm that holds the packages. There's 6 of them. So as far as tying back to our original requirements, what's mainly being targeted is requirements 8 and 9, which has to do with the system being able to carry packages up to 1.25 pounds. Additionally, requirement 1, which has to do with the overall weight, comes into play just with the weight optimization of these parts. Of course, analysis B is all the green sheet calculations using free body diagrams and then solving for reactions, and then shear and moment diagrams, developing cross sections, optimizing deflections and stress values, and then coming up with a rough shape. Next, that would move into analysis U, which is the finite element analysis, which is verifying those results, and then performing some additional iterations of weight optimization. Those are examples of some analyses. Once analysis and design were complete, construction was started as the next phase of the project. So overall, this was largely a 3D printed project. 95 of the 161 parts are 3D printed, with the remaining being small screws, which are purchased, and springs. So an example of the 3D printing manufacturing is that of the structural frame, which is the largest piece in the project. And it serves as the mounting point for all of the other components. And it was 3D printed as a single part on the Creality CR10S Pro. And it required post-processing of all the holes and mounting points and threads to allow for assembly of the project. So the requirements, going back to those, targeted in this process would primarily be 1, 8, and 10, which has to do with minimizing weight. And the reason that 3D printing comes into this is allows for obviously lightweight plastic, and it allows for design to be highly optimized where traditional manufacturing would not allow such complex geometries. And also pertains to requirements having to do with structural strength. It needs to be able to carry up to 1.25 pounds, and this comes into play is that the 3D printed layer properties are very important to structural strength. So that is an example of a manufacturing process. So once construction was complete, it was time to test the project. So the first test had to do with finding the weight, which is requirement 1. Next one had to do with being able to mount the system without any use of hand tools and modifications of the drone, requirements 3 and 4. And the third test had to do with packages, proper sizes, being able to fit inside, which is requirement 9. The fourth test was determining if the system could release packages when it was landed. The fifth test was being able to determine if it could release packages when in flight. And these two tests were requirements 6 and 7. The sixth test was determining if the system could carry the max payload, and this was a flight test, going up to 2.25 pounds. Test number 7 was determining the maximum distance that the drone can travel with the max payload, and also with the minimum payload, and of course this is requirement 8. Test number 8 was determining how much force it took to activate the system's trigger mechanism and the average number of cycles required, which goes back to requirements 2 and 5. Test number 9 was determining if the drone can hold or retain the packages when traveling at the high speed of 35 miles an hour, which covers a few requirements 8, 10, and 11. Test 10 was determining the amount of force that was exerted by the drone's camera rotation, of course requirement 2. And finally, test number 11 was determining the drone tilt angle at which the mechanism would be inadvertently released. This is just testing that, and it covers requirements 8 and 11. One of the main issues encountered during testing was that of the drone flight instability, which is tests 4, 5, and 6. And this has to do with relating to requirements 7, 8, 9, 10, and 11, and some of these pertain just to flight in general. And requirement number 8 is having to do with structural strength, being able to carry that package. So these issues, the first one was continuous upward flight. That was test 4 and 5. After takeoff, the drone would continue to fly upward, presumably without any stop. This was solved by disabling those sensors. The next issue was that of forced oscillations. At high payload weights of 1.25 pounds and more than that, the drone began to experience very high oscillations, oscillating so violently until the package was jarred out of place and released prematurely. And this was solved by disabling the IMU, or Internal Measurement Unit, and disabling the GPS. And the results of the tests are quite extensive, but some of the key takeaways will be as follows. So it was predicted the maximum allowable weight for the system was 7.2 ounces. The actual system was 5.39 ounces, which is actually 25% below that number. As far as maximum capacity goes, the system was able to reach the initial requirement of 1.25 pounds with 100% success. Additionally, it was able to carry up to 1.75 pounds and 2.25 pounds with success rates of 62.5% and 60%, respectively. As far as distance goes, when loaded with 1.25 pounds and an 8x6x3 package, which is the largest size, the drone could travel up to 4 miles on a single battery charge, which is actually 4 times the predicted 1 mile. And when loaded with a 3.75 ounce 3x3x3 inch package, the drone could actually travel up to 6 miles. There were other results, but it is better to actually look at the success or failure of the requirement to get a better view of that. So, did the project succeed? Well, as far as requirement 1, which is the weight requirement, that was passed by 25%, a good margin. Requirement number 2 was passed by a high margin. Requirement number 3 was easily passed, and including number 4, and those were the 2 that had to do with mounting. Requirement number 5 was less of such a high success. This had to do with the number of cycles to release. The average number of cycles to release was 3, and it did it 82% of the time, so it was 82% of the time was above the minimum of 1. But the range was very high. Number of cycles ranged from 1 to 5, occasionally spiked up to 15, and this inconsistency is due to friction rather than the original design using a multi-stage ratchet. Requirement number 6 was passed quite easily, as was number 7, which had to do with the success rate of releasing the package when landed and when in flight. Requirement number 8 was far exceeded, as the drone was able to carry up to 2.25 pounds, far above the 1.25 pound requirement. Requirement number 9 was easily satisfied. It had to do with fitting the packages into the system, the sizes. Requirement number 10 had to do with the drag forces at high speed, and the system sustained very well. Even with multiple crash landings, the system was still intact and did not experience any serious damage. Finally, requirement 11 was in fact a failure. Now this had to do with traveling at high speeds. With the small package size, success rate was 71%, which means during the times that it failed, it released prematurely in flight. With the 8x6x3, success rate 53% is far below the margin, as was the previous one. This margin was 75%. And at such high speeds, there's multiple reasons for this, but vibrations mainly cause the very light trigger mechanism to release prematurely. So, 10 out of the 11 requirements were passed successfully with 1 failure. So, as far as the budget goes for the project, the initial proposed budget was around $60, and after changes throughout the quarters, this came out finally to be $128. The final expenditure was $173. As far as schedule goes, the project is currently in the very last milestone, and this has to do with fulfilling all of the final requirements for senior project. And the amount of time currently put into the project is 597 hours, and expected to be, when finished, around 650 to 700 hours. So, in summary, again, this project was mostly successful, and it satisfied 10 of the 11 original requirements. However, there was still much work that has to be done, especially on the trigger mechanism, which is the main issue to do with that 1 requirement failure, and with issues even in the requirements that did pass. But the concept was still proven that a purely mechanical package release system could be designed and built, and some aspects of this project were far exceeded the initial predictions, such as being able to carry a maximum payload up to 4 miles. And with further development, a viable product should expected to be produced. So, if you have any questions, just send me an email, or feel free to check out the website. And thanks, and have a great day.